All right, I'm going to have some comments on homework 5, and then, a final exam review, hopefully really quick, and then something about Flash. Let's look at homework 5 first. I have posted the solution to homework 5 online. I don't have the solution for the layout, but just for the calculations. There's something you need to know. First, we have had about 3 model files, C5 underscore models.txt. So this one is fabricatable. So there's a company, it's a foundry, it's a pure play foundry. I'm going to explain this to you maybe on Wednesday. It's a pure play foundry called Global Foundries. It's not the biggest, but it's pretty big. You know, it used to run C5 technology. It's been over 30 years. But now they just discontinue the service for MOSES, so we cannot fabricate C5 anymore with MOSES. And what's the threshold voltage for C5? And what's the VDD we have been using for C5? You know, we used to use 5 volts for VDD, the power supply, and the VTH. You can find it in the model file, but I think it's somewhere around 800 millivolts. You know, the PMOS can be a little bit higher, but they're similar. So this is a 0.8 volts threshold voltage level for C5. And I have to use, I don't have another name for this model file. It's always C5 underscore model.txt. And then there's another one, it's called models.txt. It's the same as a CMOS edu underscore models.txt. They are exactly the same files. The reason I make it shorter is because every time I have to type such a long name, I just make it shorter. I just directly rename it. So these model files are from Dr. Baker's CMOS book. And they are not fabricatable. So there's no foundries on this planet can fabricate that 1 micron. Or 15 nano. Technologies for you, right? So these are just for educational purposes. And what's the VDD for this 1 micron technology? 5 volts, right? So what about VTH? It is 0.8 volts for NMOS and about 0.9 volts for PMOS. It's pretty similar to the C5 technologies. That's why if you do not have this one available when you're simulating all these 1 micron technology transistors, it's probably you can just directly transfer everything to this when we are trying to fabricate it. This is just for simulation purpose. What about this one? The VDD is way lower than the other ones. It's a 1 volt technology. And VTH, I couldn't remember exactly, but it's somewhere around 0.3 volts for NMOS. And I couldn't remember what's the voltage for PMOS, but you can see that it's significantly lower than all these 1 micron and C5 technologies. I just want to clarify all these model files available for this class, and so you're not getting confused. So the C5, the CMOS book, textbook from the Dr. Baker's CMOS textbook, that one does not have any information for the C5 technology because it's is not supposed to be published. You know, even though it's a really old technology, but still, whenever people are getting a contract to fabricate all the C5 chips, they have to sign what's that called? Non-disclosure agreement, NDA, right? So they are not supposed to disclose any of the details of the C5. That's why it's not showing up in the textbook, and that's why all these, you know, these educational processes are being used for simulations in the textbook. So you know the threshold voltages, you know the Cox values, mobilities, and pretty much everything about these transistors. That's the first thing I want to clarify, and the second is, let me see which is that problem. I think that's number so 1B, I guess. 1B. So dimension of the PMOS is not given in the table. Okay, so that is, what's the size of that one? You know, for all the ones given in the table, they are 30/1. Not confusing you further. So know what's going on here. 1B. So this is 20/20 PMOS, but however, in the table, it's 20/1. So how can I know this is for a short channel, not the long channel? I've told you here, right? So it's a short channel CMOS process. So you don't want to use the long channel ones over here. It's going to show up in the final exam. Just pay attention to it, right? So if I'm saying it's a short channel, it's going to be a 50 nanometer technology, not 1 micron. And long channel is 1 micron. That's a 30-year-old technology. But the 50 nanometer technology is, although it's an educational purpose, right? It's not for fabrications. But however, for something similar in the industry, which is the 65 nanometer technology from TSMC, I think that one was launched in 2005 or somewhere around that. So it's not really old. It's pretty good, actually. And so you can see the parameter given here is 20 by, for PMOS is 20/1. But however, this is 20/20. So when you are trying to find a resistance for that transistor, or RP, you just want to directly use 3.4K times 20 or divided by 20. Because this one is 20 by width and 1 by length. And 1 means 50 nano, right? So that's a scale. Or that's a scalar. So it's 1 times 50 nanometer. But let's just don't worry about the 50 nano. Just look at the multiples. So it's just 20/1 is 20/20. So definitely this guy will be longer or shorter than this guy. Yeah, same width, right? But however, the one on the table is only 1. The one shown in B is 20. So it's longer. When it has the same width, 20 times longer in terms of length, then the resistance will be what? 20 times higher or lower? 10 times low, resistance. Resistance. I think I made a mistake in the solution, did I? Oh, lower, yeah, lower. Wait, 20/20, 20/1. Yeah, lower. It's actually, no. They have the same width. And yeah, it should be larger actually. Yeah, sorry, I made a mistake in the grading. it should be 3.4K times 20, right? And for the capacitance, it should be larger because the area is 20 times larger. So RP will be 3.4K times 20, and CP will be, COXP will be 1.25 femto times 20 as well. Okay, that's for number 1B. They have the same width.
What if it was? Like what if it was
30 over 1, then it's lower. Larger. Because it has just simply has a larger area. Larger. Yeah. Yeah, if I take some points off, just let me know. I can put it back on your gray sheet. Okay, next. For the ring oscillator RC model, I think that is number 2, number 3. Yeah, draw the resistive capacitive digital model and estimate the oscillation frequency of the 7-stage ring oscillator. And you don't have to draw all the 7 stages, just to draw the interface between the first one and the following one. So just draw something like the following. Number 3. So the capacitor looks like this. And the first one definitely has the input capacitance. There's no connection because that's a gate. There's a connection. That's for the first inverter, and you got the second one. Is there a connection in between these two? Do you want to connect them together? Yes, because that's a connection here. Okay, so that's the output. So this input capacitor here is what? If you want to label it, just label it. If you don't want to do it, that's fine, because you're only looking at this point. So all the capacitors involved into the time delay here at this point will be these 4, and the resistors are this one or this one. Depends on you are looking at THL or TLH. So what's the capacitor here as the output of the first inverter? The COXP or 3/2 COXP? This one? So this one has Miller effect. So it's going to be this. Okay, so it's very clear if you draw the model like this, it's very clear how much capacitance are involved and how much resistance is involved as well. If you're doing TPLH, you want to use RP. If it's TPHL, you want to use RN. So this is the only thing you need to draw, even in the final exam, right? Any other questions regarding the homework 5? No?
What is the calculation for average power from
That's 25 microwatts. And you don't need to worry about the capacitance inside the transistors because it's relatively smaller compared to the load. So just look at the load. It's how much? Like 2 pico, right? Now looking at the table, all these capacitance of the transistors are in the femto level, so the picofarad is way higher than these ones. You can directly ignore this capacitance in there. So the load capacitor will dominate. Okay. The final exam. I got 7 problems in there. It's 120 minutes. Seven problems. Calculator is allowed. It's allowed to use during the final exam. Is that from 9:45 to 11:45 on Wednesday? Yep. $100 points. Anything else regarding this? Any other questions? No? So the first problem, so let's just look at the topics I want to cover in the final exam. So the first one, stick diagrams. It has to be one string. So all the PMOS and NMOS has to be done in one line. So if I have ABC or, let's do ABC, or DF, like this. So that is 3 transistors in parallel on the top, right? ABC. So they are analogic in NAND, should be in parallel on the top. So for all these 3 transistors in parallel, what's the strategy to lay it out? 1, 2, 3. You have 6 in total, so I'm going to include more. 1, 2, 3, 4, 5, 6. How to do it? 3 transistors in parallel. There are not too many patterns, right? It can be either 2 in parallel, 2 in series. In series is super simple because the line is already in series, right? But in parallel, it can be 2 in parallel, 3 in parallel, 4 in parallel. That's too brutal, probably not. All right, so how to do 3 in parallel? Just remember that. Done. Let's see if this is right. This is correct. So you introduce the line from the top. So definitely you want to draw the AOI logic first. That's A, B, C, D, E, F. And then in series, okay, ABC in parallel. Introduce the signal from the VDD. 1, 2, 3 in parallel. Is it correct? And these 3 signals will be merged at this node. So short it, so you can implement it, right? So you can realize that. And that signal will be merged, the final output will be at this point. So this node will be this node. And there will be another 3 transistors in parallel, which is in series with the previous one. So just start it over again, just treat this one as this one, right? So you get a signal starting from here. You just do this. Done. So that's the final output for the PMOSes. 1, 2, 3, 4, 5, 6, 7. That's even easier. Okay, that's it. And do not connect all the gates together. So I couldn't see any of the wires. It's too many wires. Just label it. Okay, just label A, B, C, D, E, F, like that. Any questions on this? Don't forget to simplify it first. Okay, if you can simplify, just simplify. Cross-sectional views. So C5 layers. I found it super boring to draw that grayscale color, grayscale top view for you guys. I directly probably will grab a snapshot from any of the layouts in the lab reports or the lab instructions. So you'll see a colorful picture with a layout. It can be a multiplexer, it can be a transmission gate. I'm going to randomly draw some of the dashed lines top of the top view and ask you to draw the cross-sectional views. So that can involve all the metal layers and all these N+ active layers, right? Digital models. So that contains ring oscillator. What is FOSC? I should close it. And more about transmission gates, right? Time delays, TPHL, TPLH, how to calculate all these values. And the question can be a little bit different. For example, if I ask you, I need this kind of frequency to drive the circuits, can you design a ring oscillator to implement it? So, for example, I tell you I need at least 500 megahertz, and eventually you calculate it and find out you need probably 5.4 inverters. Have to think about, do you want to pick up 5 or 6? So if you have more inverters, are you going to have a faster oscillation or slower oscillation, and why? And then, oh yeah, one of the problem here. I should write it down actually. The clocked circuits. Especially the clocked D flip-flop, time delays. I gave you an example in one of the lectures, I think last week or 2 weeks ago, I forgot. So definitely check that example. So it's not in your homework assignments, but definitely check out that problem. Just keep in mind, if I just keep the transmission gate in one state, when I'm looking at the time delays, you cannot have the transmission gate to be both on and off, right? It's either on or off for some of the transmission gates. And you are not including any of the time delays from the off transmission gates. So just ignore them. So only the ones are involved into the transmission. So the gates has to be on. And you have to think about, do you need to calculate, or if it's a transmission gate, is there a Miller effect involved or not? If it's a transmission gate, you pull the input on to the VDD, and the output will be put to VDD as well, right? Just one VDD, so there's no Miller effect. But for the inverters, it does have Miller effect. So the clocks will be totally different. I have exactly the solution on the lecture notes. Just definitely check out that notes and just watch the video if necessary. And number 5 will be SRAM, DRAM, flash. It won't be any calculations involved, but just trying to ask you how to operate the SRAM or DRAM or flash. You need to understand how that is being clocked and operated. And also you need to understand what is fabless, what is IDM, and what is pure play. I'm going to cover this week. So fabless means the companies who are not fabricating anything. They design digital circuits. Examples like Qualcomm, Broadcom, Apple. I believe Tesla do some fabless stuff as well. They have their engineer design all the digital chips as well. They're not just buying all the chips from Qualcomm. So IDM means integrated devices manufacturer. So they do both, like Intel, Micron, and anyone else, TI, right? So TI has their foundries as well. Pure play are the foundries, have no design teams, but only fabrication. So they can focus on fabrication, they can do it to the best job in the world because they are not getting distracted from all the digital designs. It's just do foundry. You know, what are these foundries? Who are these foundries? TSMC is the best. Global Foundries, right? It's in the US. Anyone else? So I'm going to cover this on Wednesday. So you need to know pure play, IDM, fabless. And what is Moore's law? I will cover this on Wednesday. I forgot when, but this guy predicted the number of devices can be integrated into the certain area on the chip, IC chip, will be doubled every year. It was like that for the past 20 or something years, but it's getting slowed down because it's reaching the limit. Right now, if it reaches a 3 nanometer technology, and what's the size of one atom? You cannot fabricate anything which is smaller than one atom, right? It's not possible. So the size of an atom is somewhere around 0.3 nanometer, and 3 nanometer, 2 nanometer technologies are only like tens of atoms. It's going to reach a limitation. But in the past, it starts from one micron technology or even larger, like 3 micron technology, until 5 nanometer technology. It was about right. So you need to know what is Moore's law. Just describe it. I'm going to cover that. You can Google it. I'm going to cover this on Wednesday as well. So when people are asking what is Moore's law, you just need to know it after you take this class. Right? And the timeline for the commercialization for all these technologies is good to know. I want you guys to know. I think if you memorize it before the final exam, you can probably keep it in your mind for about a couple weeks. But after that, you will probably forget everything. But still, when people ask you about the timeline for the technologies, you still have a concept. You're not telling people, hey, 20 nanometer technology was from the 90s, right? After this class, you need to know this general common sense. Commercialized. So what are these 180, 65, 22, 10, and 5? It doesn't have to be accurate. So I'm going to cover this on Wednesday or Friday. And it can be plus minus 1 year. But if it's like 2 or more years off, I will probably take some points off. Okay. Sometimes when you are talking with someone in a conference, you want to know something, right? If you're not if you want to be a IC engineer, pretend to be an IC engineer first before you become that engineer. And the last one will be number 6. BJTs. Yeah, just one problem. It's very similar to the ones being covered in the homework assignments. So why is only 6? I didn't cover the SRAM. Oh, this 6 will be. So this is actually 2 problems: SRAM DRAM flash description, and this is problem 6. This is problem 5. Let me do it here. All right, 7 problems. So the sorry DC is not covered. It's not going to be covered in the final exam. Anything else we cover in the beginning of the semester will not be covered here. It's a superposition, since we don't have time to just test you everything. So only these 7 problems. Any questions before we move forward? Hmm? What is 5? Just something like this. Hmm? Yes. Yeah. Yeah, and also in problem 5, you need to know what are SRAMs. There are acronyms, right? So you need to know the full name of them. Flash doesn't have a name. SRAM, DRAM, SDRAM. So what are they? Right, that's the final exam. We're done. That's the last week for the semester. How do you like it? Okay. Be fun. So the first week, I got exhausted because everybody was in the lab. I got to help everyone. And after you guys know that it's not required to attend the labs, and everybody was doing this remotely, that was way easier than me compared to the first week. If I keep working for about 6 hours in the lab, I will have a little bit headache physically, not mentally. I don't know why. It's probably because I was in the high energy for too long time, such a long time. I will feel pain in my head sometimes. I was feeling like I'm getting sick. So I have to go and run for 1 hour to get recovered, to get sweated, and then I can recover or do some push-ups. If I don't do that, I feel next day I'm gonna get sick. Especially during this pandemic, I got nervous about that. So that's why I started jogging starting from last August. I pretty much do about 2 to 3 runs, sometimes 7 runs a week. Depends on if I have enough energy to do it. And I feel I'm way healthier compared to a couple of years ago. Starting from last August, it's at the very beginning, I couldn't run for too long. I have to stop and take a break. But now I can run about 4 miles without any stop, and I can get it done within 22 minutes. And it's just getting faster and faster. I'm feeling really good. When you are used to something, it's really difficult. It's going to be hard to stop doing that. I think this applies to everything. If you are used to program some of the algorithm from lead code every day, I think you will probably don't want to stop at the end of the days. You just keep training yourself with all the algorithm and get a job. Or PCB design. So how long you haven't done any PCB design? That was last year. Right? So imagine that if you are going to open up Eagle PCB every day and trying to make a little bit different, literally adding some updated circuits to your old design, probably now you have a really good product already. Just want to be used to something, and then you can keep learning. All right, we have 15 minutes. We can cover Flash. Flash is everywhere. The reason is it's just a non-volatile. And your USB drive is Flash. The SD card is Flash. It's all Flash. So it's good to know it. And you have seen that it's a non-gate. It's not non-gate. It's a NAND Flash. It's just everywhere. When you are looking at the news, you can see like Samsung, Micron have their NAND have their NAND Flash memories. Blah 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 blah. Right? It's just everywhere. So NAND Flash memory is not using NAND gates. It's using a NAND logic. So let's start with erasable ROM. ROM stands for read-only memory. However, whenever it is erasable, it's not ROM anymore, right? But it's still called ROM. So that's why it has an acronym which is EROM. It is ROM, but it's erasable. Okay. It uses a floating gate technology. So the benefit of using binary is you do not have to memorize all different values. You just need to tell the computer there's a difference, right? So you just need two states, one state and another different state. Then you can let the computer to define which state you want to define as 1 and which one defined as 0. Then you get a memory. So that's the benefit of using binary numbers. So the floating gate looks like this. One gate, another gate. You got two gates. And if this is NMOS, that's a P sub. By doing something, you can attract electrons to the first gate. So what are these two gates? What are these two layers? How these are fabricatable in a CMOS technology? How can I make two gates? What are the polys? Yeah, poly 1 and 2. So that's poly 1. That's poly 2. If you can add a high voltage, it cannot be a small voltage. It has to be a pretty high voltage. And you have to short these two together. And the ground here, yeah, it has to be 20 volts. If you just apply 5 volts, it's just turning the channel on, but it's not doing anything else. If you apply 20 volts to the gate, and you can see this is a source or drain, doesn't matter. But it turns out that these two terminals has a pretty high positive voltage, which is going to attract the electrons. It's going to turn on the channel. So electrons are going to flow in that direction, right? Because of pretty high voltage, and electrons will flow. And because the electrons are being attracted or are flowing in a pretty strong electric field, so some of the electrons will just jump into the poly 1 layer and being trapped in poly 1. So these electrons are called CHE as a channel hot electron. So what's going to happen if you attract electrons in the poly 1? And poly 1 is not being directly switched by any of the voltages here. So if you are not using 20 volts, use 5 volts trying to turn it on, it's still being applied to poly 2, but not poly 1. Poly 1 is not being connected to anywhere. That's why it's called floating gate. Floating. It's just used for trapping electrons. So if electrons are being trapped in poly 1, what's happening? What you think? How can you tell the difference? Keep in mind, in digital circuits, it's in binary. It's a binary word. So you don't have to tell a continuous variations of numbers. It just needs to tell the different states. So now you got a different state, definitely, because it used to not have any electrons in there, but now it has electrons in there. So how can you electrically tell they are different? And which is interesting, if you trap all the electrons in poly 1, they will stay there for a really long time. So that's why it's non-volatile for flash. And that's why if you program your Arduino, you program it, and the program can stay there if you just turn it off. You disconnect from the power supply, right? So the individual chips, there's no power supply. And the next time you power it up, you can still see the same program because they are being programmed, so the states are being memorized by the floating gates. They're flash. Okay. For the data being stored in the SRAM and DRAMs, they're just temporary data. For example, the ones being used in cache. Doesn't matter if you haven't taken computer architecture in the past, but it's just a random. It's just a temporary memory pretty close to the CPU. Whenever it's doing the calculation, just store the data in there temporarily. And also for the RAM cards, all the RAM cards you plug into the motherboard, they cannot memorize anything if you disconnect them from the power supply. Right? These are DRAMs. But flash is different. Flash can memorize things. The reason is they can trap the electrons in there and hold that state. So what's making any differences in here? How can we electrically tell it's different? So if you have electrons being trapped in here and we are trying to turn it on, the symbol for this floating gate NMOS transistor looks like this. You have two gates, right? And that's VGS and IDS. For the normal NMOS, it has a threshold voltage. It's a threshold voltage. For example, for the C5 technology, it is 0.8 volt. If some electrons are being trapped in here, are you expecting this curve being moved to the right, being shifted to the right or to the left? And why? So briefly, if you trap electrons here, are you increasing the threshold voltage or decreasing the threshold voltage? And why? So for the normal NMOS, you connect a positive voltage to it, which is the VGS. It is doing what? It's inverting that channel. Remember? Why it's inverting the channel? Because it's a positive voltage. It's going to attract the electrons from the sub to flow to the channel and form a channel. And whenever you give a VDS, it provides a pressure, and it's going to pump these electrons to that direction. So you get a current flow. That's how the NMOS works. So in order to create a channel, you need to invert that channel first to create a channel. Right? You need to invert that area to create a channel, electron channel. So you need to invert it. You know, you can imagine there's kind of effort in there. I want to invert it. How do I invert it? I need to give a positive potential to it to invert it. But now, when you are trying to invert it, invert what? Not inverting the poly, invert the channel. When you are trying to invert a channel, there's something is doing some opposite effort. Can you imagine? Just think about if there are not electrons trapped in poly 1, and there are some positive charges, holes, being trapped in poly 1. And if you have enough charges, enough holes, and you don't even need a VGS, it's positive enough to invert the channel. So holes are helping inverting that channel, right? So oppositely, the electrons are canceling that effort. So the threshold voltage will be shifted to the right, to the left. This curve, right? So we're getting a higher threshold voltage. So now you can tell, you can electrically tell the difference. Why? Because if it is programmed, which means you have trapped electrons into poly 1, then you get a higher threshold voltage. If you're just applying a VGS just right here, which will not turn on the program, the device, but just turn on this one. So we're going to see a current flow into the NMOS, but not here. I'll tell the difference. So the programmed ones will give you 0. Current. And the not programmed ones will give you a, will conduct the currents in the channel, so you can see a current flow. I mean, I don't care how do you process it. You can invert this one to 1. It doesn't matter. Depends on how you design the circuit. But now I can definitely tell a difference. And now we're done because it's binary. If I can tell a difference, I can assign either of the state to 1 or 0. And now I get data. Right? Okay. So cover more details on Wednesday about flash and then DRAM and then whatever I need to cover for the final exam.